Hello and welcome to my YouTube channel. Here we are with the third question answer session. Let's see what questions we have in this session. So the first question is about why carbon is used as a standard for relative atomic mass. The second is about the relative acidity of methanol and water. The third is about the oxidation state of oxygen in superoxides. And the fourth is about the effect of the crystallite size on the properties of nanoparticles. We will answer these questions in this session, so let's begin. Right, the first question has been asked by Muqaddas Khalid, and she asks why only carbon is used as a standard for comparison in relative atomic mass. Now, carbon is not the first element that has been used as a standard. Historically, if you see, hydrogen and oxygen have also been used as the standard in relative atomic mass or calculating or determining the relative atomic masses of elements. But there were certain discrepancies due to which their use as a standard was discontinued and carbon later was selected as the standard for the relative atomic mass. The mass defect in carbon is zero, so there won't be any discrepancies when you calculate or determine the relative atomic masses of different elements relative to carbon 12. Due to the small mass of hydrogen, the defect was too large, so it was discontinued. Oxygen, if you take oxygen 16 as the standard, it will give a different result than if you take an average atomic mass, like considering the isotopes of oxygen, that is 17 along with 16. So the relative abundance is much higher. So the discrepancies were too high, and that is why carbon now is taken as the standard for determining or calculating the relative atomic masses of different elements. I hope your question is answered. The second question has been asked by Suleiman, and he asks why methanol is more acidic than water. Now, when we look at the structures of methanol and water, you will see that they can donate a proton. So if a methanol molecule donates a proton, it forms methoxide ion. And if water gets rid of a proton, it forms a hydroxyl ion, which are the conjugate bases of both methanol and water respectively. Now, when we talk about the acidic character or the acidic strength of a molecule, what we do is that we compare the conjugate bases of these molecules. So the conjugate base of methanol is methoxide ion, and the conjugate base of water is hydroxyl ion. And you see that hydroxyl ion is a much stronger conjugate base as compared to the methoxide ion. Now, you'll think that methyl group attached to oxygen or the oxyanion, that is an electron donating group. Of course it is. And so it should increase the negative charge on oxygen, making it less stable or more reactive or a stronger conjugate base, making its acid a weak acid, which is not the case. Methanol is slightly more acidic as compared to water. Now, why is the methoxide ion a weaker conjugate base as compared to a hydroxyl ion? The reason is that the electron density on oxygen increases if we have electron donating groups attached to it, or if we have lesser electronegative atoms attached to it. Now, in methoxide ion, the atom that is directly attached to oxygen is carbon, and in hydroxyl ion, the atom that is directly attached to oxygen is hydrogen. And if you compare the electronegativities of carbon and hydrogen, carbon is slightly more electronegative as compared to hydrogen. Its electronegativity is about 2.5, and that of hydrogen is about 2.1. So it's slightly more electronegative as compared to hydrogen. And it will not give this shared pair of electron easily to oxygen, or this shared pair of electron will not be more closer to oxygen in case of methoxide ion than in hydroxyl. So that is why hydroxyl is a much stronger conjugate base, which means the acid is weaker. Methoxide is a slightly weaker conjugate base, and so the acid is stronger. I hope you got answer to your question. Let's move on to the next question. How can, and it's been asked by Suleiman again, how can we justify the minus half oxidation state of oxygen in superoxide? See, superoxide has two oxygens joined together through a single bond. If you compare it with O2, that is oxygen, double bond oxygen, you see that there are two bonds between oxygen atoms and two lone pairs, four electrons on non-bonded electrons on each of the oxygen atom. Superoxides are formed by the reduction of this oxygen. Now, what is reduction? That is addition of electron. So if this dioxygen like O2 gets an electron, it is converted into a superoxide. And superoxide basically it's a radical anion. So if you look at this structure of O2 and the superoxide, you will find that an extra electron is added, which makes this pi bond cleave homolytically. So one electron goes towards one oxygen, the other goes towards the other oxygen, and one of these two oxygen gets the extra electron from outside. So one of the oxygen gets two electrons, one from the pi bond and one from outside, so it gets a negative charge, and the other one has a radical. So there are two lone pairs along with a single electron in form of a radical, and the other has actually six non-bonded electrons, two its lone pairs and two, one from the pi bond and one from outside. So it's actually a radical anion. And this negative charge, this -1 charge over the whole O2 in this case, or this radical anion is distributed between the two oxygen atoms, and so each one has a -half oxidation state. I hope you got your answer. Right, the next and the last question has been sent by Shima, and she asks about the effect of the crystallite size on the optical properties and the catalytic properties of nanoparticles. Obviously, the crystallite size affects different properties associated with nanoparticles. May it be the magnetic properties, the catalytic properties, the optical properties. So if the crystallite size is too small, the particles are super paramagnetic. If they are formed from, say, iron oxide, nanoparticles are formed which are magnetic in nature. So if the size is too small, they will be super paramagnetic. And if the size gets higher, if the size gets larger, then the magnetic properties also vary. Similarly, the optical properties and the catalytic properties are also affected by the crystallite size. So if you have a smaller crystallite size, it means larger band gap, and so the catalytic properties would vary. A larger size may have a different band gap, smaller band gap. So again, the catalytic properties will vary, and also the optical properties will vary. So the size, the morphology, and even the shapes of these nanoparticles, they affect different properties associated with these nanoparticles. So I hope you got answer to your question, and we're done with all the questions. For rest of the viewers, do send your questions on the email address given below. I'll be waiting for your questions. See you next time, next Friday, with new questions and some new knowledge. Thank you so much for watching.